Alright, in today's video we're looking at introductory calculations in our acid-base unit. To understand what we're going to do here, you should already have talked about or looked at the definitions of pH and POH. These are a series of 4 different equations. The definition of pH was the negative logarithm of the hydronium concentration. Sometimes it'll say the negative log of the hydrogen ion concentration. It means the same thing essentially. Now that's the definition of pH. If you know the hydronium concentration, you can calculate the pH by taking the negative logarithm of that using a calculator. Now, using the rules for logarithms, for those who've studied it in your math class, you know that you can change the logarithmic equation into what's called an exponential equation, and that's what I've written below. So there's the equivalent equation, but it's rearranged. The concentration of hydronium is equal to 10 to the power of negative pH. So if you know the pH of a solution, you can calculate the hydronium concentration in the solution by taking 10 to the power of negative pH. So a solution whose pH was 5 would have a hydronium concentration of 10 to the power of negative 5 molarity. If the pH is some other number, like 2.73, then 10 to the power of negative 2.73, you'll need a calculator to evaluate that exactly. Now, analogous to pH, we have POH. POH just means to take the negative logarithm of the hydroxide concentration. So you'll notice there that the P in pH and the P in POH must mean to take the negative logarithm of something. So when you see pH, it's the negative log of hydronium, and POH, the negative log of hydroxide. We also talk about pKa's, the negative log of a Ka value, pKw, the negative log of the Kw value. Now, there's also the inverse of that equation. The hydroxide concentration equals 10 to the power of negative POH. So we see these sets of equations are very similar, one for pH and one for POH. When we talked about the self-ionization of water at 25 degrees Celsius, we saw that its equilibrium expression was the hydronium concentration times the hydroxide concentration equals what was called the Kw, the equilibrium constant for water's self-ionization. At 25 degrees, the constant is 1.0 times 10 to the minus 14. Now this is true for any aqueous solution. So any solution where there's water involved, the hydronium concentration in that solution times the hydroxide gives you this constant value, which means that those two concentrations are inversely proportional. If one of them were to double, the other one would end up being half as big. The pH plus the POH equals 14 at 25 degrees Celsius is just another version of this equation right here. So we showed in an earlier video the derivation of that. Again, it relies on an understanding of logarithms, but if you were to take the negative log of both sides of the Kw expression, you can derive with a few steps the equation we see there. So pH plus POH equals 14.00, which is true again at 25 degrees Celsius because this 14 comes from the 10 to the negative 14 in the Kw expression. So using those 6 basic equations, 1, 2, 3, 4, 5, 6, we can fill in a table like this. If you give me any one of these 4 quantities, tell me the pH, I can calculate the POH, the hydronium, the hydroxide concentrations. If you give me the hydronium, I can tell you the hydroxide, the POH, and the pH. Tell me any one of those 4, and I can calculate the other 3. So take a moment, if you think you know what you're doing, to pause the video and try these things for yourself. If you pH is 8.15, calculate the other 3 quantities, etc. I'm going to do that for you in a moment, so pause the video if you want to try it yourself first. So the first line of the table told us that the pH was 8.15. So pH is 8.15. And I'm looking for POH, the hydronium, and the hydroxide. Well, knowing the pH, if I consider the 6 equations that I have, if I know the pH in the solution, then this equation would let me easily find the POH. It's going to be 14, take away the pH. Alternatively, up here, if I know the pH of a solution, I guess that's this equation, if I know the pH, I can find the hydronium by taking 10 to the power of negative pH. So I can find hydronium and I can find POH very easily when I know the pH value. So you can use either approach. So the easier one is just to use the fact they add to 14. So I can say that POH will be 14.00 minus the pH. So that's 14.00 take away 8.15, which is going to be 5.85 is the POH value. Now, if you wanted to use the other equation, then you would have said there that the, sorry, I'm getting ahead of myself. The other thing we could have calculated was the hydronium concentration. So the hydronium concentration, H3O positive, will equal 10 to the power of negative pH. So that's going to equal 10 to the power of negative 8.15. And so now I'm going to grab my calculator and evaluate that. If you have your own calculator, get it out and try this yourself. You can pause the video while people are getting their calculators if you need to, if you're watching this in class. So on your calculator, you find the logarithm button. On the graphing calculator, it's over here. And right above the log button, there's this 10 to the power of x. So that's what I want. I want to take 10 to the power of negative pH. So I'm going to take the second function on the calculator and then press the log button. And on your calculator screen, it should now say 10 to the power of something. So negative, the negative sign on the calculator. Be sure you're pressing the negative button and not using the minus symbol over here. Okay? So 10 to the power of negative 8.15 equals, and we get this number, which, be careful, look at the very end and you'll see it's got this E negative 9. A lot of students just write the number out front and don't notice at the end that it's actually written in scientific notation. So this says 7.08, or really 7.1. I'll talk about that in a moment. 7.1 times 10 to the power of negative 9, and this is a concentration, so molarity is going to be the unit. Now we remember in class we talked about the fact that when it comes to pHs and POHs, the number in front of the decimal, so in this case the 8, is not considered a significant digit. Only the numbers in the pH that were after the decimal, or the POH, are counted as significant digits. So when you say the pH is 8.15, there's really only 2 significant digits in that pH, the 1 and the 5. And that's why in my concentration down here, I kept only 2 digits in the concentration, 7.1 times 10 to the minus 9. Now, a note about units for pH and POH, because they're logarithmic functions, they have no units. So for pH and POH, pKw, pKa, there are no units because they're logarithmic quantities. But concentrations, as we know, will have units of molarity. So now we have the POH and we have the hydronium. We just need to get the hydroxide concentration. So the hydroxide concentration, we actually have 2 ways we can get it. If I know the POH, which I do, I can take the hydroxide concentration as being equal to 10 to the power of negative POH. Right? So that's using the equation that we saw earlier over here. Hydroxide is 10 to the negative POH. But we also saw the Kw expression has hydroxide in it. So we could also say that the hydroxide equals the Kw, 1 times 10 to the minus 14, divided by the hydronium concentration, which we also know. So we could say or, and you really only need to do one of these, but be sure you know how to do both. we could say that the hydroxide concentration equals the Kw divided by the hydronium concentration, right? So the first one is going to equal 10 to the power of negative POH, so negative 5.85. Grab your calculator and try to evaluate that. So again, you're going to use the second function logarithm feature. So second function log 10 to the power of, and then negative 5.85, and I get 1.4, and then I look over at the end, E minus 6. So 1.4 times 10 to the minus 6 molarity is the concentration of hydroxide. Now let's see if we get the same answer using the other equation. So using the Kw expression, we get 1.0 times 10 to the minus 14, the Kw at 25 degrees, divided by the hydronium concentration that we calculated above, 7.1 times 10 to the minus 9, equals, and on your calculator be sure you're using the scientific notation button, so 1 times 10 to the power of negative 14 divided by 7.1 times 10 to the power of negative 9 equals, and sure enough it's the same answer, 1.4 times 10 to the minus 6 molarity. So whichever method you use at the end for finding hydroxide, you should get the same answer. Alright, the second line of that table told us that the hydronium concentration is equal to 0.021 molarity. So using that information, we're going to go find the pH, the POH, and the hydroxide concentration. So looking at our 6 equations, we're wondering which of the equations include the hydronium. Well, looking up here, we can see the very first equation. If you tell me the hydronium, I can calculate the pH easily. pH is the negative log of hydronium. Also, as we just saw a moment ago, the Kw expression has hydronium in it. So if you tell me the hydronium, I can find the hydroxide concentration by taking Kw divided by the hydronium. So you can do either one of those as your first step. So I'm going to do the pH, it seems most obvious, so the pH definition, negative logarithm of hydronium. Be sure when you're doing your assignments, your homework, and definitely on tests, you always write the formula down like this before you put any numbers in. When you do that on your homework assignments and on other worksheets, you're learning the equations rather than just having to memorize them at the last minute before the test. So we take the negative logarithm of 0.021, and let's grab our calculators. So again, make sure you're using the negative symbol, not the minus button. So negative logarithm of 0.021 equals, and 1 point, now how many digits should I keep here? The concentration had 2 significant digits, 0.021. So in my pH, I'm going to keep 2 decimal places. Only the decimal places in the pH and in a POH are significant. So 1.68 will be the pH that I record. Now I said the other thing you could have calculated if you knew the hydronium, you could have calculated the hydroxide ion concentration right away because we have the Kw expression. Rearranging the Kw expression, the hydroxide will equal the Kw divided by the hydronium. Equals, again, we assume we're at 25 degrees Celsius. That's the temperature we'll always be using. So 1.0 times 10 to the minus 14 divided by the hydronium concentration of 0.021 molarity. Now, if the temperature was not 25 degrees Celsius, then you could still use the equation, but the question would have to tell you the Kw at this other temperature, and then you would just use it instead of this number 1.0 times 10 to the minus 14. So typing it in, 1 times 10 to the negative 14 divided by 0.021 equals a hydroxide concentration of 4.8 times 10 to the minus 13 molarity. Okay, now just a couple of things to notice so far. When your concentration of hydronium is larger, so 0.021 was reasonably large, then the hydroxide concentration will end up being very small. Okay, when one is large, the other is very small. Similarly, back here, when your pHs are above 7, then the pOHs will be below 7, and vice versa. If the pH is below 7, the pOH will end up being above 7. Okay, so those are two little things to keep in mind. Now the last thing I needed was the pOH, and we have two ways to find it. If you know the pH value already, we have it right here, then we could say that the pOH is equal to 14.00 take away the pH, since the pH and pOH add up to 14, again at 25 degrees Celsius. So that's going to be 14.00 minus 1.68 is going to be, let's see, going to be 12.32 will be the pOH. So again, notice that when the pH is low, the pOH ends up being high. Or we could calculate pOH from its definition. Because we know the hydroxide concentration, we could have said the pOH is the negative log of the hydroxide concentration, which is the negative log of 4.8 times 10 to the minus 13. Grab your calculator. The negative logarithm of 4.8 times 10 to the negative 13 equals 12.32. Again, there were two significant digits in the concentration, so I keep two decimal places in the pOH, so 12.32. And it's the same answer that we got using the other equation. Alright, if you think you know what you're doing now, pause this video, and if you haven't already done it, pause the video and try the next two on your own, and then play the video to see how you did. So the hydroxide concentration is 3.7 times 10 to the minus 5. Go find the other three quantities. And the pOH is 7.00. Go find the other three quantities. Alright, so I'll do this a little bit faster maybe. So this is the third line of the table. We know that the hydroxide concentration is 3.7 times 10 to the minus 5 molarity. So I look at my 6 equations. What can I do if I know the hydroxide? Well, if I know the hydroxide, I can find the pOH, the negative log of the hydroxide. If I know the hydroxide, I could find the hydronium using the Kw expression if I like. So I can do either one of those things. So I'll find the pOH first. pOH is the negative log of the hydroxide concentration, the negative log 3.7 times 10 to the minus 5 molarity equals, on my calculator, negative logarithm of 3.7 times 10 to the power of negative 5 equals, keeping two decimal places again, 4.43. 4.43 is my pOH. The second thing I could have calculated was the hydronium concentration. It's going to equal the Kw, 1.0 times 10 to the minus 14, divided by the hydroxide concentration. So that's going to equal 1.0 times 10 to the minus 14 divided by 3.7 times 10 to the minus 5 equals, with your calculator, 1 times 10 to the negative 14 divided by 3.7 times 10 to the negative 5, 2.7 times 10 to the negative 10. This is a concentration, so molarity. And again, we notice when the hydroxide concentration is less than 10 to the negative 7, bigger than 10 to the negative 7, then the hydronium will end up being less than 10 to the negative 7. So there's this balance. When one of them is bigger, the other gets smaller. Now that I know the pOH, the last thing I needed was the pH. And again, we have two different ways of finding this. We could take the pH definition, the negative log of the hydronium concentration, or we could use the fact that when you add pH and pOH, you have to get 14. So the pH will equal 14.00, take away the pOH value that we've already found. So using the first method, the negative logarithm of the hydronium, which was 2.7 times 10 to the negative 10, or we could say that pH is 14, take away 4.43. Grabbing the calculator, we should get the same answer, either method. So negative logarithm of 2.7 times 10 to the negative 10 gives me 9.57. And then 14 take away 4.43 is 9.57. All right. The last one told us that the pOH was equal to 7.00. Well, this is a neutral solution, isn't it? So this one actually I could do in my head. We could do all the work that we just showed above, but this one's very easy to do in your head. If the pOH is 7, then the pH, since they have to equal 14 when added together, the pH would also equal 7. pH plus pOH equals 14. I could do the little inverse. If I know the pH, then the hydronium is going to equal 10 to the power of negative pH, so the hydronium concentration is going to be 1.0 times 10 to the negative 7 molarity. Since I recognized that the solution was neutral, then the two concentrations of hydronium and hydroxide have to be equal. And so there's several ways to make shortcuts. Of course, you could have done your calculation showing all your work like this, but with those numbers, it was a lot easier just to quickly do them in my head. This would be a way to do it quickly on a multiple choice question. This is what you would do if you were doing a free response question on a test. All right, so that concludes acid and base introductory calculations. We're going to be using those calculations in further problems later, but these will be the icing on the cake of a big equilibrium problem. So we'll need to do a big equilibrium problem in acids and bases. Then at the end of the equilibrium problem, we might calculate the pH, for example. So this is the foundational calculations in the acid-base unit.